Dear students, today we'll see what do we mean by differential pulse code modulation, that is Dpcm. Okay. Now here, if you see our previous concept of Pcm, if you have taken a wave like this, and if you have taken samples which are moreover near to the Nyquist criteria sampling rate, where Fs was equal to 2 FM, twice the highest modulating frequency, sampling frequency is equal to twice the highest modulating frequency, you will get one sample here, one sample here, one sample here, one sample here. And these samples you will quantize and encode it in binary data, and you are going to send that sample value. Say for example, this is 1 volt, this is 2 volt, this is 2 volt, this is 1 volt. All that will be converted into binary data, and that you are going to send in your Pcm, pulse code modulation, what we have seen earlier. Now if you see Dpcm, we can have the same type of waveform. And here we can also increase the sampling rate, because here we will not be worried about our data bit or bandwidth which will get increased, because in Pcm, if you increase the number of samples, the number of data bits will increase and the bandwidth will increase. So here in Dpcm, we can increase the sampling rate. Say for example, sampling rate, we can put it as 3 FM, 4 FM, 5 FM, 6 FM, 7 FM, 8 FM, 9 FM, anything. Say for example, we put it as 7 FM. 7 times the modulating frequency. Then you can see samples which are very near to each other. Okay. Now what happened in Pcm was, every sample value we had quantized, and after quantization we had taken a fixed value and we had encoded that binary data, and we had sent that amplitude value in terms of binary, and we had sent it. So there the bandwidth requirement and the data rate requirement depends upon number of samples you have. Now here we have increased the number of samples. That means they are highly correlated to each other. There is more information coming. Okay. And the first thing what we do in a Dpcm is, we are not going to send the amplitude value in binary form. We are going to take the difference of the previous amplitude and the present amplitude. Say for example, this was our previous amplitude and this is our present amplitude. Now the previous amplitude, say it was 1 volt, and the present amplitude, it is around 1.5 volt. Okay. Now here the difference between 1 volt and 1.5 volt is 0.5 volt. So we are not going to send 1 volt or we are not going to send 1.5 volt. We are going to send the difference between them. The difference between them is 0.5 volt. We are going to quantize that 0.5 volt, encode that 0.5 volt and send it. Similarly, if you come to the next amplitude, say this is 1.8 volt. So when you are going to send this, we are going to take the comparison between the previous and the present, and the previous and the present gives a difference of 0.3 volt. And that 0.3 volt we are going to quantize, encode and send. That means always whenever we are having a present amplitude, we are going to compare it with a previous amplitude, and what is the difference between them, what value comes, that we are going to quantize, encode and send it as binary information. So we are not sending the actual amplitude values, we are sending the difference between two amplitudes. That is why here the quantization levels also will decrease, and the number of bits you are going to send will also decrease, because quantization level will decrease because the value itself is less. Difference value is always less than the actual amplitude value. That means we are always going to send a lesser data rate. So our bandwidth also will be less. This is the first thing. Data rate, data bits will decrease and our bandwidth also will decrease as compared to PCM. Because we are not sending actual amplitude value. We are sending the error between the present value and the previous value. This is first thing. The second thing is, if you observe this part of the waveform, if you observe this part of the waveform, this we have taken it as 1.8 volt. This will also be 1.8 volt. This will also be 1.8 volt. This will also be 1.8 volt. Now in this case, if you take this as present value and this as previous value, the error between them will be 0. Otherwise, if you take the next one as present value and this as previous value, the error between them will be 0 because both are of same amplitude. Now in this case, it will, there is no need for you to send it. There is no need for you to send it because it is an error, because the error is 0 over it. Now in this case, all this same values amplitude will be taken as redundant information. Redundant information. Only the first one and the last one you can take because in between all are having same values. It is redundant information and this redundant information can be eliminated. So it is compressed. Whatever is not required or whatever is not varying much, whatever is having same values, same value amplitudes for a longer time can be compressed. That means redundant of information is eliminated. Redundancy in information is eliminated. This is second advantage of Dpcm. That is, whatever is unwanted, whatever is not changing for some time, it is not sent because it is having same value. The amplitudes, the samples are having same values. So that there is no need for you to send it. So those redundancy of information can be eliminated. Okay, this is the second advantage of Dpcm. So the first advantage was the data bits and the bandwidth required was less. And the second advantage is redundancy in information is eliminated. So these are the two advantages of Dpcm, which makes it much better as compared to PCM. So based on this, we can go to see the next block diagram of Dpcm transmitter. Dear students, today we'll see what is Dpcm transmitter now. Now here I have shown the block diagram of Dpcm transmitter. Now here the basic concept is that whatever sampled input we are having of the actual signal, that every sample will be compared by its predicted value and the error between those two will be quantized, encoded and sent as Dpcm wave. Now here if you see, this is the actual sampled input what we have shown, input xt. So it will be your analog signal where every sample will come as an input. Now that every sample will be compared by its predicted value. Here you are showing a prediction filter. This is an important stage of Dpcm transmitter, which makes it better as compared to PCM. Now this prediction filter is one which will predict from the previous inputs, from the previous samples as to what the present sample should be. So it will give a predicted value. That predicted value is called as x cap t. Now this predicted value and the present value will be compared in this subtractor. In this subtractor they will be compared and the difference between them will be called as error, and that error will be quantized. It will have a fixed value which will be called as EQT. That will be encoded, that means converted into a binary data or digital data, and that is sent as a Dpcm wave. This is what the basic process of Dpcm goes. Now here the most important thing is, what is this prediction filter? The prediction filter will get its input from the previous quantized error. It will, this quantized error and the predicted value will be added and given as a quantized value to this prediction filter. This prediction filter will give an output of a predicted value, what should be the value of the sample to come, and that predicted value is compared with the actual input value, and the error between them is quantized, encoded and sent as a Dpcm wave. This is what we had seen in the basic concept of Dpcm. So this is the explanation for block diagram of Dpcm transmitter. Dear students, now we will see what do we mean by Dpcm receiver. Now we have shown the block or diagram over here. This is the input what we have got from the transmitter section. That was your Dpcm wave, and first it is given to a decoder. That means the input binary data which is in electrical form will be converted to an quantized fixed value of amplitude. So these samples will be converted into a quantized fixed values of amplitude. So it is called as EQT. Now that EQT is added from a predicted value. The same type of prediction filter we had used in transmitter also. Now in receiver also we are using a prediction filter which will give you an output called as X cap T. Now that X cap T is a value to which this error value which had come from the transmitter is added. And after adding to this, the value what you get will the actual sample value of the present sample. So that sample value in the quantized form will be called as XQT. If you pass that through a low pass filter, XQT will become XT, which will be a smooth analog signal. Now that will be your main information signal what you have first sampled and sent. So that will be the output of the Dpcm receiver. So here our prediction filter is again an important stage which is going to give you an X cap T. That X cap T will be added to the error which has come from the transmitter. Both if you add, you will get the actual sample value, and that if you pass through the low pass filter, you will get a smooth wave which will be the recovery of the original information signal. So this is your Dpcm receiver.